The problem says, if 6.022 times 10 to the 23rd people are gathered, and the average person has a mass of 160 pounds, what is the mass in kilograms of that group of people? That's a question. Next part of the question, compare this value to the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. Is it smaller or larger? So there's a bunch of stuff here. And when you read, and this doesn't even look like a chemistry problem. It doesn't. It's a unit conversion problem. What you're going to find is that most chemistry problems end up becoming unit conversion problems. And so we have to learn how to do that process where you cancel the units to get to the answer, because almost all chemistry problems will be solved that way. So you have a certain number of people gathered, a gigantic number, 6.022 times 10 to the 23rd people are gathered, and you want to figure out what is the mass in kilograms of that group of people. Don't try to map out a path to the answer. Instead, what you do is you write down what is given to you as the first step in the conversion process. So you are given 6.022 times 10 to the 23rd, and you have to put a unit here. In this problem, it says people. People are gathered, so that's what you write, people. Do not be afraid of using your own units. In this case, people is not a chemistry unit. That's okay, it's still a unit. And you see how you put it in your conversion, kind of like your conversion table. And you put it in there because that is what is given to you. That is like the starting line of a race. You always know what's given to you, so you always put that down first. And you don't try to figure out all the way how to get to the answer. Instead, you ask yourself, okay, I want the mass in kilograms of people, but I don't know how all the way to get there. But the other information it tells me is the average person has a mass, really the weight, of 160 pounds. Now that's not what we want because we want kilograms, but we know how to go from the number of people, which is written on the board, to the number of pounds, because we are given another conversion factor. The average person has a mass or a weight of 160 pounds. So what we can do is we can go to the second part of the conversion process, and we can say that one person is 160 pounds. And I'll put LB for pound. Now, when you write these unit conversions, you can flip them over any way you want, but we arrange it this way because people will cancel with person. Now, this is a little bit of a gotcha. The word people is a little different than the word person, but you know that this is this many individual persons. I guess you could put persons here to cancel with person, but it's referring to the same thing, a human. That's what it means. And if you stop the calculation right here, then what have you converted? We've taken this very large amount of people multiplied by their average weight, and the total answer we would get would be the number of pounds that entire crowd of people collectively weighs. But that's not what we want. It says we want to know the mass in kilograms. Now here's where you have to go and figure out, is there a conversion factor between pounds and kilograms? I don't have it memorized, but you can look it up either in your textbook or some other reference, and everybody can figure out, using available references, what is the conversion between pounds and kilograms. And roughly 1 kilogram is 2.2046 pounds. Now, why did I arrange it this way instead of flipping it over? Well, it's because pounds on the top and bottom, they will cancel. If I stop the unit conversion process here, all of the units have canceled except for kilograms. So I read my problem statement. So many people are gathered. The average person has a mass of 160 pounds. What is the mass in kilograms of the group of people? The only unit left in this conversion problem is kilograms. So you know that you must have arranged the units correctly. All right, and it was a multiple step process. So what you do is you say, what is 6.022 times 10 to the 23rd? You multiply by 160 and you divide by 2.2046. Now really you're multiplying and dividing by 1, but that doesn't do anything. So multiply and then divide, and what you're going to get is 4.370 times 10 to the 25, and the only unit left is kilograms. So this is actually the answer to part A of the problem. What is the mass in kilograms of that group of people? All right, relatively simple. Most of you would have been able to solve this even without using unit conversions in a table, but I'm telling you that you need to get used to writing it like this in this table and canceling units, because very soon I will give you a problem that's too complicated for you to do in a different way than what I'm showing you. So I'm showing you an easier problem so that you will get used to doing it this way. You're going to have to trust me. We're going to use this for balance, for calculating chemical reactions, for calculating heat released in a chemical reaction, for calculating all kinds of things in chemistry. So we're doing it this way. Now the part B of the problem said compare this value to the mass of the Earth, and it gives the mass of the Earth. So how do we compare things? You could put an inequality symbol, which one's bigger and smaller, that's fine. But a better way to compare two numbers to see which one is bigger and how much bigger it is to take the ratio. So let's take the mass of the group of people, and let's divide that by the mass of the Earth. Right? If the mass of the people were exactly equal to the mass of the Earth, for instance, then we would get a number of 1, and we would know they would be exactly equal. If the mass of the people were exactly double the amount of the mass of the Earth, we would get a number of 2. So by taking the ratio, we can see, is it 2 times as big? Are they equal? Are they 3 times as big? Is it 4 times as big? Which one is bigger and by how much? All right, so what we have, the mass of the people is given by 4.370 times 10 to the 25. That's kilograms. And the mass of the Earth was given to us is 5.98 times 10 to the 24 kilograms. Now these units are here and they're divided, so the units are really going to cancel away. So at the end of the day, when you cancel this, you just get a ratio, a number that doesn't have any units because these kilograms really cancel. So if you take 4.370 times 10 to the 25 divided by 5.98 times 10 to the 24, you get 7.31. So what you have figured out from this answer is the people are 7.31 times, I guess I don't want to use the letter X, times the mass of the Earth. So basically 7 times more massive. So you could compare it a different way. Obviously, you can see that the mass of the people is bigger than the mass of the Earth. By dividing them, you can see how many times bigger. It's a little bit over 7 times bigger. Now, you might argue this obviously is not even a chemistry problem. That's okay. The goal of this is to get you used to the unit conversion process, essentially. All right, now we have 3 parts to the next problem. They're all really small, but they're all very, very important to understand how to accomplish. So here we go. Perform each of the following calculations. The first one says, what is the mass in grams of 0.3460 moles of zinc? What is the mass in grams of 0.3460 moles of zinc? So don't try to map anything out. Don't try to think, oh, I'm going to multiply, divide. Just forget it. What you do is you write down what you have been given. That's all you do for the very first step. I'm telling you, it will save you time. Absolutely. So let's jump in and write down what we are given. We are given the number 0.3460 and it's moles of zinc. Now notice I did not write 0.3460 moles. I did not write 0.3460 zinc. I did not write 0.3460 atoms or whatever. I wrote 0.3460 moles of zinc. When you are doing these problems in chemistry, you must be explicit. If you're talking about moles of something, you say moles of whatever it is. If you're talking about atoms of something, you say atoms of whatever it is. If you're talking about molecules of water, you don't just say molecules, you don't just say water, you say molecules of water. You have to be explicit in everything you write, otherwise you will get confused when you're canceling units. So please take my advice. Now this is the number that's given to us, so we just write that on the top of the conversion factor. Now, we want to know what is the mass in grams. So we know this is going to involve moles, we know it's going to involve grams. So we go to the periodic table, right? We go to the periodic table and we take a look at zinc. So let's go find zinc on the periodic table. Where is zinc? Right here. Element 30, which is atomic number 30, and the atomic mass is 65.39. Now, since we've learned about molar mass, the way you really interpret that is zinc is 65.39 grams per mole. That's how many grams exist in 1 mole of zinc. So it links the unit of grams with the unit of essentially atoms of zinc, which is what the mole represents. So 65.39 moles. So that's basically a conversion factor. The periodic table is full of conversion factors. So what we could do is we could say, just to be explicit, we could say the molar mass of zinc, as given by the periodic table, is 65.38 grams per mole. right? 65.38 grams per mole. This is a conversion factor because it means there are 65.38 grams in 1 mole of zinc. That's what this means. So we are going to arrange this in a way that's going to be beneficial to us. So what we're going to say is 1 mole of what? We're talking about zinc. So it's 1 mole of zinc is equal to or equivalent to 65.38 grams. Grams of what? Grams of zinc. Right? Now we arrange it this way, so moles of zinc exactly cancels with moles of zinc. The only unit left is grams of zinc. The problem says exactly the mass in grams of 0.3460 moles of zinc is what? The only unit I have left is grams of zinc. And so I know that it has to be multiplied like this. So what I'm going to do is I'm going to take 0.3460, I'm going to multiply by this number, and then I'm going to divide by 1. So when you take 0.3460, multiply by 65.38, then what you're going to get is 22.62, and the unit left over is grams of zinc. 22.62 grams of zinc. And you might notice something. Some people pointed out, wonder why I do it. Notice all of my Z's have a little slash through them. Slash, 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 slash. Why is that? It's because it's something I picked up in engineering school, right? It's because if you start writing Z over and over again without it, then they start to look like 2's, right? This looks a lot like a 2, so you don't know if you're scribbling, is it a 2 or is it not? So get in the habit with your Z, drawing a little slash, and you will always know that these are Z's, and these will always look like 2's, even if you're writing very, very fast. So what this means is that if you measure out 22.62 grams of zinc in a lab, you will know that you will have exactly a little bit more than 1/3 of a mole, 0.3460 moles of zinc. All right. Next problem, here we have to do the calculation. How many fluorine atoms are in 2.620 moles of F2, which is the fluorine diatomic molecule? We want to know how many fluorine atoms. Now there's a lot of stuff going on here because we're given the number of moles, but it's the moles of the molecule. The molecule is F2. There's actually 2 atoms in there. But we want to know how many individual atoms are there. So there's a lot of steps to the problem. There's moles, and then there is atoms, and then there's Avogadro's number, and then so don't try to map it out in your head. Just forget it. Just write down what you have been given and be explicit with writing down exactly what you have been given. And what we have been given is we're trying to convert 2.620 moles. So you don't want to say just moles. Moles of what? Not moles of fluorine, because that's not what the problem says. Moles of F2, the diatomic molecule fluorine, right? Because fluorine doesn't really exist, it's just an individual atom. If it bumps into another fluorine atom, it's going to bond and form a molecule. So we have, basically, we have 2.620 moles of the bonded diatomic molecule, right? Now we want to get to atoms. We can't go from moles to atoms because this mole is not referencing atoms. It's referencing the molecules that are 2 of them bonded together. So if you don't know exactly how to get to the answer, just do the next thing in sequence that you can do. You know that you have moles there, so I can convert from moles to molecules because 1 mole of anything, in this case it's 1 mole of the fluorine diatomic molecule, is what? 6.022 times 10 to the 23rd, and you have to be explicit. I want you to write molecules of F2. You see, this is why we spent so much time learning about Avogadro's number and understanding what it means, because when you say you have a mole of calcium, let's say, then that's atoms it's referring to. But if it's a mole of F2, it's 6.02 times 10 to the 23rd molecules, which is two fluorine atoms together as a unit, 6.02 times 10 to the 23rd of those units, okay? But we are not interested in molecules of F2. We want to know how many atoms are there, right? So what you can say is, we have the unit. If we cancel these units, the only unit left is molecules of F2. We don't want that. We want to know something about the atoms, right? So what you can do is you can say that 1 molecule of F2, 1 molecule, just 1 single molecule of F2 is equal to 2 fluorine atoms. You see how I've written down a unit that cancels top and bottom? And this is exactly true. It's something you know. If you have F2, then one of these molecules is equal to 2 of these fluorine atoms. And now, since I can cancel the molecules of F2 with the molecules of F2, the only unit I have left is fluorine atoms. Go back to your problem statement. How many fluorine atoms exist in this many moles of whatever it is? And so this is the multiple step problem we have to then solve. Right? So what you do is you take 2.620, you multiply it by 6.022 times 10 to the 23rd, and then you multiply by 2. Of course, you're dividing by 1 2 times, but that doesn't change anything. So multiply this, multiply by 2, and then what you're going to get is 3.156 times 10 to the 24 fluorine atoms. So you see, it's a little tricky at first because you are given the number of moles, so people think, oh, you just multiply by 6.02 times 10 to the 23rd, but that's going to give you molecules. You still have to multiply by 2 because there's 2 fluorine atoms in every one of those molecules. So 3.156 times 10 to the 24 fluorine atoms. All right, let's take a look at the next one. Let's calculate the number of calcium atoms in 28.50 grams of calcium metal. So again, do not start in your head and say, oh, I'm going to do this, and then divide, and then multiply, and then try to figure it out. No, just forget it. Just write down what you have, and then you incrementally get a little bit closer to the answer as you go. And what have we been given? We are told that we have 28.50 grams of calcium, grams of calcium, right? Those are atoms. So I can just write grams of calcium. And you draw your long little conversion bar right here. And what are we trying to actually do? We're trying to calculate the number of atoms, right? So how do we go from grams to atoms? We can't go directly, but we can go from grams to moles because the molar mass is how many grams are in a mole. So we can go to the periodic table, right? And we look up calcium. Calcium is right here. And it's element number 20, and the mass is 40.08, and that unit is grams per mole. That's the molar mass. So I don't need to do this for every problem, but I'll just say the molar mass of calcium works out to be 40.078 grams per mole. And let's just double check, that does match with this. Okay, so how can I use that up here in my conversion factor? Well, I can say, since I have grams of calcium, I'm going to put grams down here, and this is the number, so it's got to be 40.078 grams of calcium in 1 mole of calcium, right? Or 1 mole of, let me put a capital C here so we don't think it's something else. Calcium. So the grams of calcium cancels the grams of calcium. So you see, we use the fact that it's 40.078 grams per mole. We blow it out to match the units a little bit better. That 1 mole of calcium atoms, is equal to 40.078 grams of calcium. That cancels here. If we stop the calculation, then we have landed at the moles of calcium. How many moles do we have? Right, but we don't want to know how many moles. We're trying to calculate the number of atoms. Now we know the conversion between what a mole is, 6.02 times 10 to the 23rd atoms. That's what a mole is. So you can say then that 1 mole of calcium is 6.022 times 10 to the 23rd. And since we're talking about calcium, it's not a molecule, it's just atoms of calcium. And we just continue that guy out. Right, 6.022 times 10 to the 23rd atoms of calcium. So we cancel the moles of calcium with the moles of calcium. The only unit we have left is the number of atoms of calcium that we have. All right, and so we come down here and finish the calculation and say 28.50. Then we multiply by 1, which does nothing. Then we divide by 40.078. Then we multiply by 6.022 times 10 to the 23rd. Then we divide by 1, which that part doesn't do anything. And what do we get? We get 4.282 times 10 to the 23rd calcium atoms. So you see, it gets very confusing if you try to do this in your head. If you try to think, well, I've got grams of calcium, so then I'm going to go calculate, divide to get, to get moles, and then I'm going to then go and multiply to get atoms. And what if there was another step in there where there was a molecule involved and you had to multiply by something else? Then it would be too many things to carry in your head. So what you do is you write down what you're given and say, what can I convert to? What am I legally allowed to convert to? And I know that if I know grams of anything, I can always find the moles because the periodic table tells me how many grams are in every mole of everything on that table. So I can always get to moles. Then when I get to moles, I'm like, oh, well, then I can just go from moles to atoms, and that's what the problem wants, and I'm done. All right? All right, we only have 2 more. So let's go over here and do the last 2. Now for each of the following 2 problems that we're going to do here, we want to calculate the mass of sodium contained in an 8.5 gram sample of what I have here. So I have 2 things that I have here. The first one is an 8.5 gram sample, 8.50 gram sample of sodium chloride. And then we have another one down below we want to do again. So what I want to do is I want to figure out how many grams of sodium are in this amount, 8.50 grams of sodium chloride. So for each of the following samples, calculate the mass of sodium that is contained in an 8.5 gram sample. And so I've just given you the first one, sodium chloride, 8.5 grams of that. All right, so what are you going to do? You have grams of sodium chloride. Well, what do? Well, you want to know how many grams of sodium are there, so you start trying to play around with, well, I know it's made of 1 and 1, and you start trying to kind of guess your way through it. What you need to do is do what you know how to do. I know how to calculate the molar mass of sodium chloride. We've done that, and that tells me how many grams are in every mole of sodium chloride. So then once I have moles of sodium chloride, then I will examine the next steps, but I don't have it mapped out in my head. If you try to do too many things in your head, then you're just going to turn into spaghetti, and you're not going to be able to, you're going to be paralyzed. So what I do is what I know that I can do. I know that grams of sodium chloride I can convert to moles of sodium chloride, because I can look at the periodic table and I can find the molar mass of sodium chloride, right? Which would be the mass of sodium and the mass of chlorine. So if I go and look at sodium, it's 22.99, and the mass of chlorine is 35.45. Both of those are in grams per mole. So I'll use extra digits as I usually do. So I will say, I'll say 22.990. This is in grams per mole. And then I'll add to that, because there's only one atom, the chlorine, which is 35.453. And this is also in grams per mole. So the molar mass of NaCl, when you add these 2 numbers together, you get 58.443, and that's grams per mole. And this is for the whole thing, the whole sodium chloride formula unit, ionic compound, right? So if I want to take what I've been given and go the next step in the conversion process, let's convert it to moles. So what I know is there's 58.443 grams of NaCl in 1 mole of NaCl. And I arrange it this way because the grams of sodium chloride will cancel with the grams of sodium chloride. Now this is the conversion factor that I had to calculate. So it wasn't something given to me. I had to use the periodic table to find the molar mass of sodium chloride. That's why we learned that skill first. So if I stop the calculation here, I will know how many moles of sodium chloride I have in my, in my container or whatever it is. But that's not what I want. I want to know how much sodium do I have? How many grams of sodium? All right. So what you have to do is say, well, in 1 mole of this, how many moles of sodium will I have, and how many moles of chlorine will I have? Because chlorine doesn't really matter, but you can think through it, even though you're not going to use the chlorine in this particular problem. 1 mole of sodium chloride means 6.02 times 10 to the 23rd sodium chloride formula units. But in every one of those moles of sodium chloride, there's going to be 1 mole of sodium and 1 mole of chlorine. It's like a dozen, right? If I have, I don't know, it's hard to describe. If I had like, let's take this. Pretend this is sodium chloride, right? But just call it a red marble and a white marble, and they're bonded together, or stuck together. Now I have a dozen of these things, a dozen of these units together. So that means that if I break it apart, I'm going to have a dozen of the white ones and a dozen of the red ones. Together, I have a dozen of the unit, but if I break them apart, I have a dozen of the white ones and a dozen of the red ones. So it's the same thing for this. If I have a mole of sodium chloride, that means I must have a mole of sodium and a mole of chlorine. If I break it apart, I will have a mole of sodium and a mole of chlorine. So what you then say is an intermediate little conversion step, that in 1 mole of NaCl, I have 1 mole of sodium. Okay, And I write it like this, so I can cancel the moles of sodium chloride, and then I have the final step of the conversion process. Now, if I stop the calculation and just stop here, I will have the answer that I will have here would be the number of moles of sodium. But I don't want the number of moles of sodium, I want the number of grams of sodium, right? So I can go to the periodic table and I can say, all right, 1 mole of sodium is how many grams of sodium? So I go over here, of course we already used the number, 22.99 grams per mole. We used it right here, 22.990. So I can say 22.990 grams of sodium. Now this will cancel with this. Now what unit do I have left? I have grams of sodium left. What does the problem say? For each of the following, calculate the mass of sodium they contain that is contained in an 8.5 gram sample of sodium chloride. The unit I want is the grams of sodium atoms. Grams of sodium atoms. And so you see how it gets confusing if you try to figure this stuff out in your head. You start with what you are given and you incrementally work towards the answer. So then what you say is, I guess you could just kind of come down here and finish the calculation and take 8.5 and then times 1 divided by 58.443 times 1 divided by 1 times 22.990 and then divide by 1. And the answer you're going to get is 3.34 grams of sodium atoms. And that's the final answer. So if you know the grams of the substance you have and you don't know what to do, you think about what can you do? And you say, well, if I have the grams of anything, I can always convert to moles. So I have to go get the molar mass first. So I do that. And then I use that grams of sodium to moles of sodium, grams of sodium chloride to moles of sodium chloride to get to moles. Once I know how many moles of this I have, then for every mole of sodium chloride, there's a mole, 1 mole of sodium. And then when I have it in moles of sodium, I convert from moles of sodium to grams of sodium. Now, this is the only step that looks to be a little out of place. At first, you're wondering, why do I even do this? Well, in this case, for every mole of sodium chloride, there's 1 mole of sodium, so these numbers, the ones, didn't really change anything. But what if the compound were Na5Cl? I mean, that's not a possible compound, but let's just say. Then there would be, for every mole of sodium chloride, there would be actually 5 moles of sodium. And so you would have to multiply by 5 to get the proper number. So you have to use, you have to use everything at your disposal. And if you stop here knowing moles of sodium chloride, you've got to get to moles of sodium before I can go to grams of sodium. And so you have to learn by doing. I mean, none of us are born with this. You have to see it to know how to do it. But I am going to tell you that if in your mind or on paper you try to skip ahead and say, well, I'm just going to jump over to gram, you can't do that. You have to cancel every unit there. So if you're here and you're trying to get to grams of sodium, you can't, because this is moles of sodium chloride. So you have to convert from moles of sodium chloride to moles of sodium before I can go from moles of sodium to grams of sodium. If you think you're trying to skip something, then stop, because you've messed up somewhere. All right, the next one. It's the same problem. We have a 8.5 gram sample of the next compound, and we want to figure out how many grams of sodium we have in that compound. So for this one, we're going to say 8.5 grams of the compound Na3PO4. That's grams of that. And we want to figure out how many grams of sodium are in this compound. How many grams of sodium are in this compound? So, same thing, right? We know the grams of the total compound. We know that we can convert from grams to moles of the whole compound. We don't know how we're going to map it all the way out to the end, but we know that we can go from grams to moles. But to do that, we have to figure out what the molar mass of this is. So I'm going to skip down, and I'm going to say the molar mass of Na3PO4. Now we have to calculate this molar mass. We have 3 sodiums. We've used that number several times, 22.990. So 3 times 22.990. And then we have to add phosphorus, which is P. Phosphorus, which is P, 30.97. And I'm going to use the number 30.974. Right? And then we have 4 oxygens, and we've used that one enough, so we say 15.999, and there's 4 of those. So once you take 3 times 22.990, and 4 times 15.999, and then you add it to this number and then add it to what you calculated here, what you're going to get is 163.940 grams per mole. And this is for this compound here. So then what we do is we jump upstairs and we use that to convert from grams of this compound to moles of this compound. So we know that it's 163.940 grams of Na3PO4 is in 1 mole. 1 mole of what? You have to be explicit. Na3PO4. Now this grams of this compound cancels with the grams of this compound. So it's this many grams of this per 1 mole of this. So we cancel the units. Now if we stop the calculation right here, then we land on the number of moles of this. But we can't stop there. We want to get to how much sodium we have. So how do we do that? Because if we stop, then we know the number of moles of this whole thing. But we also know that in 1 mole of this compound, there's actually 3 moles of sodium, because in one of these formula units, there's 3 atoms of sodium. So the ratio is, for one of these groupings of this compound, there's actually 3 sodium atoms. That's how we bridge the gap from moles of the compound to talking about the individual sodium, because we have the formula right here. So we know that 1 mole of this compound, Na3PO4, must contain 3 moles of sodium atoms. Sodium atoms. Okay? So then what do? We cancel the moles of this compound with the moles of this compound. All right? And so then we run out of space here. So what I'm going to do on the next line is I'm going to continue on. That's okay. You can just continue. Just pretend that this whole thing is kind of connected to the end over there. Now, if we stop the calculation here, we have the number of moles of sodium atoms. And we want to calculate the number of grams of sodium atoms. Fortunately, we know that sodium is 22.990 grams per mole. So we can say that in 1 mole of Na atoms, there is 22.990 grams of Na atoms. And it looks like I didn't need this whole thing after this, because we're basically done right here, right? Because on the bottom, we have moles of sodium atoms. And over here on the top, we have moles of sodium atoms, so those two things cancel. So what we do is we take 8.5 times 1 divided by 163.940 times 3 divided by 1, then times 22.990, then divided by 1, and the answer that we actually get is 3.58 grams. Grams of what? Grams of sodium atoms. Sodium atoms. And this is the final answer. Let me just double check myself. 3.58 grams of sodium atoms. And that's what the problem said. What is the mass of sodium contained? And so the way in which we got there was sodium atoms. Now notice how I'm being very explicit when doing the unit conversions. It doesn't just say moles. It doesn't just say grams. It says moles of the whole compound written. Grams of the whole compound written. It doesn't just say moles or grams here or moles here. It says moles of the compound, moles of sodium atoms. To remind me, I'm just talking about atoms. Grams of sodium atoms, so on and so forth. That is to keep it straight in my head. If I just write moles down or grams down, I will eventually get confused when I'm solving more complicated problems. I'll probably end up canceling something that I don't mean to cancel. Because what if you have chlorine or something else involved? If you just put grams, you won't remember what it was you're talking about. So there is a little bit of writing. But the good news for chemistry, to be honest with you, is that notice that all of these problems have just involved multiplication and division and some addition. Of course, we had to add a couple of times. But all of these unit conversion, dimensional analysis, they're all just multiplying and dividing. You know, in physics and in advanced mathematics, you have very complex equations, calculus, things like that that are difficult to pull off. In chemistry, it's mostly the concepts, and it's the habits you build to write things down in a way that allow you and set you up for success. But the math itself is easy. It's just multiply, multiply, divide, multiply, divide, multiply, divide. Okay, multiplication and division. But the devil's in the details. You have to set it up to cancel properly. Now, if you were looking at this lesson and saying, wow, I don't get it, I don't understand, I never would have thought to do this stuff, then what you need to do, because I was that student, okay, you need to watch this lesson again. And then you need to, once you watch it, you pause the lesson, you read the problem or read what I'm talking and asking you to do, and you solve it yourself while the video is paused, so that you can get your brain doing going through the motions of doing these kinds of thought processes. You can't figure it out by just watching somebody do something. You have to do it yourself. So I want you to watch me, but then I want you to do it. Whenever you write this down, you need to know I have grams of something. Okay, I can convert to moles of something because I've done it a million times. Okay, when I have moles of something, I can get to moles of sodium. No problem. I've done that a million times. All right, once I got moles of sodium, I know I can go to grams of sodium because I know the molar mass. But knowing that you can do those things, and it's like running or track or football or soccer or any kind of sport, you have to practice it. When you practice it, you will begin to see what you have to do much faster. So please, watch the lesson again, solve the problems. And we have 3 more lessons after this to get more practice with calculating with moles. So follow me on to the next lesson. We'll continue to learn how to calculate with moles. Learn anything at mathandscience.com.